John Keller. So let me tell you a little bit about him. So John Keller is also a candidate for bachelor's degree in both general engineering and physics. Got a bunch of brave guys here. He's had a lot of research experience. He started in the summer of 2010 at Harvard. He worked with a group where they looked at adapted and digital holographic microscope for the tracking and following of Brownian particles. In the summer of 2011, he did some research in the summer at Princeton University where he looked at, developed an algorithm, worked with a group that developed an algorithm for phase reconstruction in digital holographic microscopy. Continued on in summer of 2012, back to Harvard University where he worked with a group where they were primarily concerned about optimizing GPU and the high-performance GPU cross-correlator for application to large radio telescope arrays. He has further experience in designing a rocket-powered grenade launcher simulator for testing radar equipment and has been a lab instructor for the last 3 years or so in Eastern Nazarene College. The title of his talk is Optimizing Cross-Correlation on Graphic Processing Units in Radio Astronomy with Gauss's Complex Multiplication Algorithm. Welcome, John Keller.
Last summer I worked at the Harvard Smithsonian Center for Astrophysics with Lincoln Greenhill on optimizing computational efficiency, etc. And this is an example of one of the radio telescope antennas we used. So the motivation for the project comes from figuring out what the universe looked like shortly after it began expanding. So this would be maybe the first few hours, the first day of the universe, if the universe was a year long. So this is about 400,000 years after the Big Bang, which is almost 13.8 billion years ago. So that's a long distance, long time ago. And the idea is that we can use radio telescopes to analyze a signal from hydrogen atoms in the beginning of the universe. And that way we can sort of understand how it was structured and how the first stars may have began forming. You can think of the universe as a balloon. So this would be the universe billions of years ago. You can see a wave moving across the surface of the balloon. But over time, we know that the universe is expanding. We know that space itself is expanding and objects are becoming further apart without moving relative to space. Space itself is getting bigger. So we can see that on the larger balloon, the wave is stretched out. So it's almost like if you take a slinky and you pull it apart, you'll see how it just gets stretched out to a longer wavelength and lower frequency. Because this happened over the course of 13 billion years, we have a dramatic change in wavelength from about 21 centimeters to 2 meters, which is a very large change. And the frequency after the redshift, as we observe it today, is between 10 and 200 megahertz, depending on where in the dark ages we're looking. So this is what a GPU looks like. It seems really complicated, and it is very complicated. Here we have off-chip, which is the main computer, on-chip is the graphics card. You don't need to understand what all of the graph is, but you can see we have different layers of memory. As you move further down the chart, you have lower level memory. And here we have each box here, you can think of as a thread or a person doing the experiment. And then you have a group of threads here, a group here, and another group here. So groups can work together, and you can have threads working independently. Now, the reason this is all important is because we have different amounts of memory. So at the very lowest level, each thread can store data in memory, but it's a very small amount of memory, and it's a very small amount of threads that can access it. So all of these different threads, all these different workers, these different lab workers have to communicate somehow. They communicate through memory.